Thanks for your patience. We should start the morning session, and we'll start with Héctor Olivares, who's going to tell us about a simulation pipeline for nearly circular supermassive black hole binaries.
Thank you very much for the introduction. Also, good morning. So, well, today in this talk, unfortunately, you will not hear too much about lensing and about wave optics. However, I will be describing here a computational framework that I think, and I hope that could be useful to all people working on general relativistic ray tracing and general relativistic radiative transfer, and especially in the field of simulating the observational appearance of supermassive black hole binaries. So this is a work that I am doing in collaboration mainly with Roman Gold, but also with Samuel Tutul, Siri Jonesy, and with Luciano Rezzola. So, well, as you may have heard, simulation-based modeling has been really important for experiments such as the Event Horizon Telescope and also the gravitational wave searches. In fact, interpretation of these observations is many times based on trying to match what is observed to very large libraries of simulated data, which can be synthetic images or synthetic waveforms generated in different ways. Very soon, there will be other experiments. There are many of them planned for the next decade that will open even more the possibilities of the phenomena and the objects that can be observed. In particular, well, as we were hearing yesterday from Alex Luxaska talk, there will be soon at least for the next decade, probably there will be the Black Hole Explorer. Also, there is ongoing efforts to expand the array of the Event Horizon Telescope to what would be the next generation EHT. And also for the next decade, in the 30s of this century, it is expected that the gravitational wave detectors that are space-based will be launched. So this is, what you can see here is for example, the map of the different sources that are planned to be observed by the Black Hole Explorer. So you can see that we hope to see many additional shadows and also some other sources. It turns out that actually, very interestingly, many of these sources are supermassive binary black hole candidates. You can see them marked in red. And well, in addition to this experiment, there are also other supermassive black hole candidates that may be too faint to be resolved by this instrument, but which are expected to be observed in other wavelengths, and that are also candidates for multimessenger observation. In particular, there is this source that is expected to have a frequency that can be detected already by LISA. So, however, accompanying to this effort to observe more of these objects, there should be an effort to simulate them in order to predict their observable properties and their associated phenomenology. So, similarly to the libraries that we have for the Event Horizon Telescope, it would be very useful to have a library that we can use to interpret data and to study and predict the phenomenology in supermassive black hole binaries. This is, however, a bigger challenge than what we have faced for the Event Horizon Telescope. In fact, the fact that we have to simulate a dynamic spacetime complicates things a lot. However, there has been some progress especially in the past decade about how to properly simulate this using also general relativistic magnetohydrodynamics and even general relativistic ray tracing. Some highlights, there are many, several work that has been done in this respect. Actually, I didn't cite it here, but there was recently a review article by Luciano Combi that lists all of these, all of the efforts to this date. However, some of the highlights that I would like to mention are from Roman Gold, that is a collaborator in this project. This is a picture for one of his simulations from 2014. Here, he simulated the evolution of the binary with numerical relativity, and simulated on top of it the accretion flow using GRMHD. You can see here the accretion disk in this simulation. Also, you can see the magnetic field threading the two black holes, and this empty region that forms due to the motion of the binary that cleans the fluid in their path. More recently, there were these simulations by the group of Scott Noble that try to save the expensive numerical relativity simulations, and what they do instead is that they use boosted black holes. So they calculate individually the spacetime of each of the two black holes. They are boosted, and then they complete the rest of the spacetime using post-Newtonian approximation. These simulations were very interesting because actually they didn't only simulate the GRMHD, but they actually calculated also images. And you can see here this is the GRMHD simulation. This is looked from above, and here there is the image where you can see some of you can see the black hole affected by lensing. So something else that you may notice is this black spot that is here in the middle. This black spot is not a third black hole. What is it? What it is that because this simulation uses a uniform mesh, and cells become very small close to the origin of the coordinate system. Here you need to, it is better if you avoid this, because otherwise this could reduce very much the time step due to what is called the CFL condition. So they leave this region out of the simulation, and then they can evolve for very long times. More recently, even in this year, there was a very interesting work by the same group that tries to solve this problem of the origin by using what they call what is called a multi-patch approach. So what they do there is that they use a Cartesian mesh to simulate the region close to the black holes. And farther away than that, they use a spherical mesh that has the advantage that it can go to further extensions because you can use a logarithmic mesh. But here you are not bounded anymore by the small time steps that are that appear close to the origin of the coordinate system. And they report in this paper that by doing this they could reduce the cost of the simulations to 3% of the cost of the previous simulations. So it is really nice. The downside is that you have to interface the two grids in such ways that one that acts as the boundary condition of the other, and this requires some computational effort. So, having said what is the current state of the art, I would like to now show you what is the approach that we intend to use to make these simulations. So, first, we would like to restrict to a very to a much narrower subset of simulations. This is the subset of binaries that have quasi-circular orbits, and this is something very advantageous for us for simulations, because they, as we will see, they are much easier to simulate. But in addition to this, it is actually physically reasonable that this system will be in quasi-circular orbits. This is because in general compact objects, binaries are very efficient at circularizing. So it is actually it's something that we would expect. So we've then focused to the case where the binary has already circularized, but it is still losing angular momentum via gravitational radiation very slowly, and then you can consider the system as nearly well, as nearly circular for all the time. So you still don't consider the inspiral. So this is very, very good for the purpose of simulations because in this way the spacetime exhibits a quasi-helical symmetry in the phi and t direction. And you can consider the spacetime, therefore, as stationary if you choose a suitable foliation of the spacetime that could correspond to locate yourself in the co-rotating frame of the binary. This is very nice because in this way it becomes possible to use a stationary spacetime code similar to the codes that we use for the EHT collaboration. So it is also nice because avoiding the problem of evolving the spacetime, we now can use simulations that have a cost that is comparable to those in the library of the EHT. So we reduce a lot the required expense. Also, well, one additional advantage is that for the GRMHD code that we plan to use, it already has adaptive mesh refinement, so we can find more creative ways of avoiding the problem of the very large resolution at the origin. Actually, well, something that is very nice in addition to this is that the metric that we will be using is not a post-Newtonian approximation or black holes that are accelerated, that are boosted, but independently one from each other. But it's actually a solution from numerical relativity. So we obtain it using a solver that is used to find initial conditions in numerical relativity. So the approach is, well, can be divided in 3 blocks that you can see here. So at the beginning, we use a spectral solver used for initial conditions in numerical relativity. This is called Kadath. Then we interface it with a general relativistic magnetohydrodynamic code. This is BHAC, the black hole accretion code. And then we use a library that is capable of reading the adaptive mesh refinement data in order to feed it to a ray tracing code that is, in this case, the one with which we are working is called BHOSS. So and this combination has already been used to create part of the simulation library of the EHT. And then, well, the addition is essentially this part, but also the AMR library. So now I will explain a bit in more detail what are all of these steps. So, well, first, Kadath. Kadath is a public solver for systems of elliptic partial differential equations. So it is used to solve the Hamiltonian momentum constraints at the beginning of a numerical relativity simulation. And in particular, we use a branch that is called FUCA for Frankfurt Initial Data, Frankfurt University Kadath. So a paper about this branch was published in 2021 by Pappenford and Tuttle, which is also one of our collaborators. This is very nice because this package for initial data can produce binaries of unequal mass and that are also spinning. So in the data that Samuel has produced, we even have mass ratios of 100. So you can maybe you cannot reach to the regime of extreme mass ratio in spirals, but you can well have a very different mass ratios. So this tool is based on the conformal thin sandwich approach. So it is this method created by Pfeiffer in 23 and 25, and it is based on these 4 assumptions. So the first one is that you can write the metric as conformally flat. So this means that the spatial part of the metric can be splitted into the line element of flat spacetime, but multiplied by a conformal factor that is a scalar that varies from point to point. It also uses maximal slicing. So this is a condition on the extrinsic curvature of the spacetime, sorry, of the spatial slice. We also have the assumption that I mentioned before that there exists a helical killing vector. This helical killing vector, well, here it is set perpendicular to the spatial slice. So our time vector is also this helical killing vector, and therefore the metric is time independent. So there is symmetry in this helical direction. So the foliation always has the same induced metric. And finally, the last assumption is not necessary, but for simplicity, it is assumed that there is time symmetry. So this basically is to neglect gravitational radiation. So then we use the metric that is obtained from this as a background for the GRMHD simulations. And for the GRMHD simulations, we employ this code called BHAC. This is actually a code that I helped to create during my PhD. So it is a code that does general relativistic magnetohydrodynamic simulations on fixed spacetimes. It is based on an older solver for conservation equations that is called MPI-AMR-BHAC. As in name says, it is parallelized with MPI, and actually it has a hybrid parallelization of MPI plus OpenMP that allows to use a very large number of cores. Even we have tested even order 80,000 cores with still good scaling. It also has adaptive mesh refinement, which is what you can see here. So there is, you can see here the mesh overplotted on a simulation of accretion onto a black hole. The black hole is here. And you can see here that there are blocks of varying resolution. So the code can increase the resolution at places where it calculates that it is more needed. Finally, the code is, well, we try to keep this code well documented with manuals and tutorials. It has been used for the HD simulation library, and also currently there is a new version that has been developed in Frankfurt that is called BHAC Plus, that has some other very nice features. So, well, what we have to do then is to interface this code with the metric that was produced by the Kadath solver. And what we did in order to do this was to create a new metrics module. So the BHAC is already very flexible in terms of the geometry that it can use, because actually it was devised in order to consider non-Kerr metrics. So it is very modular, and the different metric modules. Well, there are different metric modules that contain all the information related to particular spacetimes. So what we did is that we added a general module for conformal metrics. And this module reads some information from the Kadath solver, and it can, but you can in addition implement very different geometries and very different coordinate systems for the spatial part of the metric. So something else that we do is that in order to have a very accurate spatial derivatives, we don't calculate the derivatives inside the code, let's say by finite differencing, but we also evaluate them from the spectral solution produced by Kadath. So this is a bit tricky because if we want to transform the spatial derivatives to the derivatives in the BHAC coordinates, we have to perform a non-tensorial transformation because the derivatives of the shift are not tensors themselves, so they are just partial derivatives, not covariant derivatives. So this is just a technical step. We do this, and then everything is good. So this is an example of how the mesh looks in two different simulations. This is the lapse function in Cartesian coordinates, and this is in spherical coordinates. So, but you can see that, well, the lapse function, of course, is the same in both places because it's a scalar. And here you can see some arrows that are representing the shift. And this is, you can see that there are all of them are rotating. And this is because what I mentioned, we are in the binary co-rotating frame. And therefore, the spacetime is fixed for us, but we see a shift that is dragging matter around the binary. So, well, I just wanted to show you quickly a simulation of how this looks for purely hydrodynamic torus. So you should, this is made in Cartesian simulation. It is for a binary with mass ratio 1 to 10. So the primary is here. The secondary is somewhere here at radius r equal 10. And you can see that, so in contrast to the black hole case where this torus should stay in the same place where you leave it, in this case, the tidal forces disrupt the torus, and well, eventually you get some kind of waves and other shocks and a richer phenomenology. If you simulate the magnetized case, you see also well, all the other very interesting phenomenology like these complex jet structures. This is for an equal mass binary, so you can see here that the jets make some braids from the rotation, and these are some cases with unequal mass and spin. Well, you can see that the structure is more disordered. There are also some more complex emission patterns. So what you can see is in this plot is Bremsstrahlung emission proxy and synchrotron emission proxy. So these images are not ray traced. They just calculated an approximation from the emissivity from the GRMHD variables. But something that is very interesting is that, for example, in synchrotron emission, you see not only the vicinity of the black hole shining, but you also see this kind of wall that comes from the spiral shock that orbits around the binary. And of course, you see, if you look in Bremsstrahlung emission, you can see also a lot of X-rays coming from this shock. Right. So then we come to the third block in our approach. This is the ray tracing code. So I should mention that this is still not properly linked to everything, well, to what is before, because as I mentioned, this is still some work in progress. But I can tell you a bit what are the plans for interfacing and what is already done. So well, BHOSS is a code that has been developed by Siri Jonesy. It also, well, it has ray tracing and general relativistic polarized radiative transfer. It has already been used to simulate ray tracing on numerical spacetimes, which is very useful. But currently, coupling it with BHAC requires a file format conversions that sometimes can take very long. Well, previously this was not so much a problem, but if you expect to make heavy use of AMR, you have to regrid many times, and this can be. So if you regrid it to a uniform mesh as it is required now, it is very expensive. So there is actually another GRRT code that is already supporting the AMR data format from BHAC. This is called Raptor. But in the way of making BHOSS capable of reading the AMR data from BHAC, we try to do something more general. Actually, we try to do something that is not only useful for BHOSS, but can also be useful for any other ray tracing code that we want to interface with BHAC. So in order to do this, we developed a reader library for the AMR format of BHAC. This, even though right now it reads just the BHAC binary format, in principle it can be also, it should be easy to make it read the, for example, HDF5 format, because the main point about this reader is not so much that it reads the format of BHAC, but is that it is aware of the AMR structure and the grid connectivity. So this means that if you split the domain in different blocks, the code will know which blocks are the neighbors of this of a given block. It will also know which blocks are the children of some given block, and it will also know what are the boundaries of this block. So, for example, if a block is next to the edge of the simulation, if it is next to a coarser block, to a finer block, or to a same resolution level block. So this, well, I will show later what is the use of this. But another important thing is that the library that we have developed has interfaces with C++, with Fortran, and with Python, so that you can call it from any application that is using these programming languages, and you will simply need to call a read, and then to call an evaluation routine to retrieve the values of the GRMHD variables and the values of the metric at some point. Finally, in the process of trying to to debug the library, we also ended developing some data visualization tools that I will show you next. Yes. Also, I forgot to mention, since this is since you can interface it with Python, you can also use it interactively. So you can use it to inspect the AMR data for instance, in a Jupyter notebook. So here, for example, I am reading the data. Then I am trying to query some information about a given block. So I am asking information about a block with these indices. I am trying to find what are the children. That is the blocks that are subdivided from the bigger block. And here I am, for example, querying what are the neighbors of some block in some directions. Why this is important? Well, for ray tracing, it becomes very important at the time of making interpolations. So here I wanted to show you also some of the visualization tools in action. So this is an isosurface plot that was generated with these built-in tools. So this is the initial condition of the torus. So it should be just a donut, but if you look at this figure, you can see that there are these cracks. So these cracks are some very annoying artifact that we always find when we try to plot AMR data with software, for example, as Visit or Paraview. But this is when it comes the usefulness of using an AMR-aware library. So normally this is avoided in other codes by including ghost zones, but actually you can also avoid this by letting the code know what are the neighbors of some batch. So here, for example, we should let the code know that this region is the neighbor of this other region. So by doing that, we can, if we make the code aware of this, we can connect the two regions so these cracks are removed. And well, in this way we can do interpolations. And here, for example, we have made an interpolation of the normal to the isosurface, and you can see that everything looks smooth. So I just wanted to show you now some examples of visualizations of the binary simulations. So here you can see the spiral shock, but rendered in 3D with isosurfaces, as you can see it here. And these are some visualizations of this braided jet from the equal mass simulation. So finally, well, as I said, I maybe was a bit too optimistic on what I could achieve before this talk. So there is still no general relativistic ray tracing, but there is a simple ray tracing that is not general relativistic. So this has also been done by launching rays and retrieving the values of the GRMHD variables at a single point, and you can use this to do some volume rendering as the accretion flow that you can see here. So well, this is the current status of the library. Then, so to conclude, I would like to well highlight that the main purpose of this was to share with you the existence and the status of this framework, so that can be used for, or that has the end goal of being used for supermassive black hole binary simulations, but that can also have a more broader use. So, for example, the interfacing between Kadath and BHAC can be used not only for these binary metrics, but in principle can also be used for any conformally flat metrics that are generated in the Kadath format. So, for example, it can be used as well to simulate binaries between a black hole and a compact object of a different kind, if that is of interest. And so, well, I also explained, I also showed some features about this AMR aware reader. So what is needed to do in the near future is to complete the coupling with BHOSS, so to add all the proper calls to the evaluations of the GRMHD variables. We also have the plan to upload these tools to a public repository so that anyone that is interested in making these kind of simulations can do it. And well, we expect that we are working towards a very interesting science outcome, which is the fast creation of libraries for supermassive black hole binary data, as well as to study the dynamics and the electromagnetically observed phenomenology of supermassive black hole binaries. So, well, this is all. Thank you very much.